Yes, obviously go check out the website. Go check out BioniChaos.com. There is a lot of it. Why is my microphone something not right? I'm just talking too quietly. That should be okay. You have to talk like, yeah, I need it in the yellow, so probably need the microphone closer to my mouth or speak louder, one or the other. So go check out the BioniChaos.com. We will be going over the tools, and this one is the most recent one. It's an actual, instead of just using AI, we're actually making AI. We actually started training this neural network model that it's a convolutional neural network trained on EEG spectrograms with and without seizures. I just realized the other day, probably the default seizure, non-seizure images should be different because yeah, this one looks like there's actually something in there, so we use one of those as default. Yeah, someone mentioned slowing. I'm not sure if it's related. So there's a slowing of spikes during seizure. There's supposedly some slowing activity prior, before a seizure actually happens. But yeah, we'll need a different data set for that because this one only includes during seizure a frequency response spectrogram. The other thing about it is only selecting one channel from multiple channel recordings. And over here, so you can slide through the original data and you can look at essentially the different runs of the training and what the results we were getting. So you have the first run, we got up to 81%. And if you just look at yeah, the confusion matrix, so it's, well, yeah, let's go one by one, shall we? So we have accuracy and loss plot. Probably have to make this bigger somehow. Anyway, we'll be likely to cover this many times going forward, so don't know why my microphone is, yeah, this is a bit better, increase the sensitivity of it, but then it might introduce all sorts of noise into the recording. We'll start again in a sec. So I don't know what are we covering. Yeah, we're doing multiple things at the same time, so bear with me. Eventually we will edit the videos into shorter ones that actually hopefully make some sort of sense. I can't promise anything. So we have, yeah, full disclaimer. What happens with the other eye? Yeah, I have to keep adjusting the threshold there for it to work. Then it kind of stops finding the pupil again. Have to remember, edit all this out if we're doing video editing later on this. Currently I have a huge backlog here. If someone wants to, by any chance, help with editing videos, there is a ton, loads of raw material. So like it's this live stream is being recorded and then hopefully edited later on, but yeah, it takes a lot of time. It will be also interesting if someone else actually editing it, because you possibly find other bits being more interesting, so that could actually, you know, change focus to something else, maybe. So what's the kind of stuff we are talking about? Yeah, we'll cover that. Let's actually jump straight into this. Just listen to it as well, so I just don't lose my voice. Have the robot helping us out.
Hey everyone, thanks for joining us on the live stream. Today, we're diving into some exciting stuff around combining different types of biomedical images, like CT and MRI scans, to uncover insights you won't see from just one scan alone. Imagine overlaying these images to get a super detailed view that shows both the bones and soft tissues of the brain. Pretty cool, right? We're talking about how we can use some clever tools and techniques to do this right in your browser, in real time, with some fun and interactive features. If you have questions or ideas, drop them in the chat. Let's explore how we can make biomedical data more engaging and accessible for everyone.
Yes, I had some question online about essentially displaying two types of images, like overlaying them one on top of another. I don't know, we will explore potentially why on earth we want to do this. Probably don't, but you know, if we can, then why not? So it giving us some ideas, but we need to, yeah, well, thread carefully, but also, yeah, I'll just start from basics. Okay, can you actually do quick responses? We're live streaming together. So we would like it to be more of a discussion. Unfortunately, we don't currently have a human to talk to, but that's okay. So yeah, tools and libraries. Yeah, using Python-based packages sounds great. Ideally, we want to eventually move everything to JavaScript, but yeah, starting with Python, that's always a good choice. So yeah, we'll need some good data set that we could use this for. Actually, can ask yeah, is there, if you can look it up, are there any suitable datasets that we could use for this? I don't know why it can't get my voice correctly. Hopefully I'm using the correct microphone. Yeah, obviously a good data set will be a really good start for doing anything, because currently we just if we can find any papers first, and ideally, so we kind of stopped reading papers that don't share the data. So if you publish your results, I believe you should also publish the data, because the whole idea behind results in the public domain is that they should be reproducible. So if you are a researcher and you're publishing your results together with the data you used, that's the right thing to do. So thank you very much for that. Yeah, if you can do quick responses, we want to have it more as a conversation. Maybe just ask questions.
Got it. Hey everyone, we're looking for data sets that would be perfect for overlaying CT and MRI scans of the same brain area. Ideally, we want data sets that are openly available and come with all the data you need to reproduce the results. Because let's be honest, if you're publishing your findings, you should share your data too. I'll check out if there are any good data sets out there that fit the bill. Meanwhile, if anyone knows of any resources or data sets that provide both CT and MRI scans for the same patients, let us know in the chat. It's all about finding the right data to get started with these kinds of image overlays and registrations. And by the way, if you're a researcher publishing results without the data, come on, let's make it open and reproducible. All right, I'm diving in to find some data sets.
Yes, it's supposedly found some data sets. It might be hallucinating. We have to obviously check each one. It's also not good at providing links. Did this actually work? Yeah, we don't like a lot of terms and conditions. I'm pretty sure we already registered with this one. Does ring a bell. We would like just stuff in the public domain. This one has an ad. Yeah, lots of ads on this website. Did mention that Oasis Brains. Right, well, that's the same link. You need to register for it, so not ideal. I don't actually want to use it. Can we search for data sets that actually do not require registration, where the data is just available in the public domain without registration or login? Yeah, want accessible data. I know, yes, there might be reasons for putting it behind a restricting access.
Hey, I found some data sets that are available in the public domain without requiring registration or login. 1. OpenNeuro is a fantastic resource that offers a wide range of MRI, PET, MEG, EEG, and IEEG datasets. It is the successor to the OpenFMRI project and provides datasets in the brain imaging data structure, BIDS format, making them easy to use with various open source tools. OpenNeuro hosts many datasets that are freely available for download without any registration, so you can start working with them right away. 2. Zenodo is another excellent platform that hosts multiple open access datasets, including various medical imaging datasets like MRI scans, CT scans, and segmentations. Many of these datasets are directly downloadable and are in the public domain, making it easy to access and use them for research or development. These platforms are great for finding datasets that are freely available, well documented, and easy to use, aligning perfectly with the goals of reproducibility and openness in research. Feel free to explore these sources and let me know if you need more specific guidance.
Okay, can we go back to the original questions? So the original topic at the beginning of this conversation, and yeah, we would like to go deeper on that one. If you can ask more questions and give a quick overview and then ask more specific questions. Yeah, while it's generating, go check out the BioniChaos.com. We might do some demos of some of the tools quickly. We have a bunch in under development. Yeah, I would like to actually focus on this cardio rock. So it's a rock curve. This one we actually were fixing it. Should have been working a bit better. Not at the moment. You're getting errors for those. Yeah, that's the cardio rock that we will be doing more work on today. Have some funny games there as well, but they don't work really well. Yeah, the idea for this was for playing a game where you can place body parts on the template. But yeah, as you can see, the body parts are not great. It's just something ChatGPT generated. We need to make them better. We were thinking actually trying what's that open source 3D rendering tool that apparently can automate using Python. I always forget. Yeah, we'll start a blog on it or something and then go from there. But yeah, we want to focus on the rock, cardio rock. We will jump into it in a second. Yeah, the bot here going places. Yeah, we need to essentially understand why we call registering a different types of imaging. That would be a good start. The other thing, it might be a bit too heavy to do in JavaScript. Yeah, you might need a dedicated software for it, so it might not be ideal as a Flask application. So couple, can you just summarize, just give the questions in a quick list, and also questions regards turning this into a custom Flask application on BioniChaos.com.
Here's a quick list of the questions. Questions for deepening the image overlay process. 1. Pre-processing. Have the images been pre-processed? Artifact correction, intensity normalization, resampling? 2. Registration method. Which registration method, rigid, affine, non-rigid, is most appropriate for your images? 3. Optimization and metrics. What optimization techniques, mutual information, normalized cross-correlation, and evaluation metrics, dice coefficient, Hausdorff distance, will you use? 4. Analysis goals. What specific analyses or measurements do you plan to perform after overlaying the images? 5. Visualization techniques. How will you visualize the overlaid images, e.g., color mapping, opacity adjustments, 3D renderings? 6. Clinical applications. What clinical scenarios or questions are you targeting with this approach? 7. Tool development. Are you planning to develop a custom tool? And how might this fit into your broader web applications? Questions for turning this into a Flask application on BioniChaos.com. 1. Integration. How will you integrate image registration and overlay features into a Flask-based application on your site? 2. User interaction. What kind of user interface will you design to allow users to upload, register, and analyze images within the Flask app? 3. Client-side processing. How can you leverage JavaScript libraries for client-side image processing to ensure a smooth user experience in the web application? 4. Scalability. What steps will you take to ensure that the application can handle multiple users and large datasets efficiently? 5. Open source tools. Which open source Python and JavaScript libraries will you use for implementing these features in a Flask app? These questions should help you structure the development of a custom image overlay tool for your website, ensuring it meets both technical and user needs. Hey everyone, let's recap what we've been exploring today. We started with the idea of overlaying different types of biomedical images, like a head CT and an MRI, to find insights that aren't visible when looking at each scan individually. The goal here is to align these images so that they provide a more comprehensive view of the same brain area, combining the strengths of each modality, like the detailed bone structure from a CT with the soft tissue contrast from an MRI. This can reveal hidden pathologies, aid in surgical planning, or provide a better understanding of the relationship between different anatomical structures. We talked about the different steps involved in this process, including pre-processing the images, choosing the right registration method, optimizing the alignment, and evaluating the results. We also discussed the importance of deciding what kind of clinical questions you want to answer with these overlaid images and what visualization techniques will make those insights clearer. We then touched on how to turn this idea into a practical application using Flask on your website, BioniChaos.com. This could involve developing a custom tool that allows users to upload, align, and analyze images directly in the browser, leveraging both Python and JavaScript for efficient processing. We also brainstormed ways to make this tool scalable, user-friendly, and fully open source. We're also looking for the right datasets to start experimenting with this, ideally ones that don't require any registration and are available in the public domain. We found some great options like OpenNeuro, which hosts various MRI datasets, and Zenodo, which offers a wide range of open access medical imaging data. So, we're diving deep into how to bring these ideas to life, making advanced biomedical imaging analysis accessible to everyone. Stay tuned and keep your questions and suggestions coming in the chat. One specific dataset that would be highly useful for your project of overlaying head CT and MRI scans is the OASIS-3, Open Access Series of Imaging Studies dataset. OASIS-3 is a longitudinal multimodal neuroimaging dataset that includes a wide range of MRI sequences, such as T1-weighted, T2-weighted, FLAIR, ASL, SIS2I, and more. It also includes PET imaging data for over 1,300 participants, covering both cognitively normal adults and those at various stages of cognitive decline, from ages 42 to 95. This dataset is particularly valuable because it includes multiple imaging modalities for the same subjects over time, making it ideal for your goal of aligning and overlaying different types of scans to derive new insights. For example, you can use the T1-weighted MRI data to get high-resolution anatomical detail and align it with CT data, if available, to see how different tissue types and pathologies overlap. OASIS-3 is open access, but it does require a data request and agreement to terms for usage. The data is well suited for developing and testing registration algorithms, visualizing multimodal imaging data, and exploring correlations between structural brain changes and cognitive function. You can access the OASIS-3 dataset and find more details about it on their websites, sites.ul.edu/. The OASIS datasets are a valuable resource for neuroimaging studies, but they come with specific terms of use to protect the privacy and confidentiality of the subjects. These terms prohibit using the data to attempt to identify or contact individuals, generating images or representations that could enable re-identification, or using or disclosing the data in ways not permitted by the agreement. Any use of the data must include proper acknowledgement and citation of the OASIS datasets, and publications using certain types of PET data must be submitted for review to Avid Radiopharmaceuticals before dissemination. Given these restrictions, if you plan to use OASIS data for overlaying CT and MRI images, you must ensure that all analyses and visualizations are compliant with these terms. This means that the data should remain anonymized, and your application or tool should not allow any attempts to re-identify subjects or produce images that could be used for facial recognition. It's essential to provide proper citations and acknowledgments in any resulting publications or presentations to comply with the dataset's usage policies. If these restrictions are too limiting for your specific project goals, you might consider looking for alternative datasets that are fully in the public domain without such requirements. For example, datasets available on platforms like OpenNeuro or Zenodo may have fewer usage restrictions while still providing high-quality imaging data for research purposes. For any proposed publications or presentations using the PET data from the OASIS dataset, specifically those involving fluorbetatapir F18, AV45, or fluortaucipir F18, AV451, you are required to submit them to Avid Radiopharmaceuticals at least 30 days in advance. This is to allow Avid Radiopharmaceuticals to review and comment on the content for any intellectual property interests. This requirement is part of the terms of use associated with the OASIS datasets to protect proprietary rights related to the PET-T tracers used in the imaging studies. If you are using these specific PET data types in your research or applications, be sure to comply with this review process by preparing your manuscripts or presentations ahead of time and allowing sufficient time for their review by Avid Radiopharmaceuticals before any public dissemination. If you prefer not to seek any approval or abide by the specific terms set by the dataset publisher, like submitting publications for review to Avid Radiopharmaceuticals, then the OASIS dataset might not be the best choice for you. The OASIS dataset has specific requirements, especially concerning certain PET data, fluorbetatapir F18 and fluortaucipir F18, that mandate a review process before any public presentation or publication. These conditions are legally binding and are in place to protect intellectual property interests and the privacy of the research participants. If you do not want to comply with these requirements, you should consider using other open access datasets that are fully in the public domain and do not require any form of approval or registration. Platforms like OpenNeuro or Zenodo offer a variety of datasets with less restrictive terms, many of which are specifically intended for unrestricted public use. These datasets typically do not have additional conditions or require prior approval for publications, making them more suitable if you are looking for complete freedom in using and sharing the data. It's important to review the data usage policies of any dataset you plan to use to ensure it aligns with your project requirements and to avoid any potential legal or ethical issues. Great choice. OpenNeuro and Zenodo are both excellent platforms for finding open access datasets that are available without the need for registration or approval. 1. OpenNeuro is a platform that hosts a wide variety of neuroimaging datasets, including MRI, PET, MEG EEG, and IEEG data, all available for free and in the public domain. Datasets on OpenNeuro are formatted according to the Brain Imaging Data Structure, BIDS, which makes them easy to work with and compatible with many analysis tools. Since OpenNeuro focuses on the open sharing of neuroimaging data, you can use these datasets without needing to seek approval from any publisher. You can explore the available datasets directly at OpenNeuro, openneuro.org/. 2. Zenodo is a general-purpose open access repository developed by CERN that allows researchers to share datasets, software, and other research outputs. Zenodo hosts many medical imaging datasets, including MRI and CT scans, and allows for easy searching and filtering of datasets that are openly accessible without registration. You can search for specific datasets that meet your requirements by visiting Zenodo, hzenodo.org/. Both platforms are ideal for projects where you want to use data freely without dealing with additional legal or administrative hurdles. Check them out to find the right dataset for your needs.
We are already using OpenEuro for one of the tools, the Brain 3D. There was a problem with it that we need to fix. Just open the project in a separate we have this structure for it. We have the images in a dataset locally, stored locally, so we're not fetching them from anywhere else. And that's the good thing about the OpenEuro, is that you can just get the data actually trying to use some of the JavaScript libraries, but from memory they didn't work really well. Yes, we have the tool on the main page, but yes, we can cycle through every direction. Some description at the bottom, so it should explain what's what. But then we meant to have the volumetric data loaded in here, and it's actually still loading. It just takes some time for some reason. From memory, the JavaScript was the JSON file that has the data is only 100 megabytes in size. Yeah, 98 megabytes in size for the volumetric data. And then we have the 256 images for each axis. So those are images, so the PNG images, so they are easy to deal with. But the volumetric data is this JSON file that is, well, first taking forever to load. Oh yeah, now it's actually visible. That's what it looks like. So it's a bit pixelated. I don't know actually why. And yeah, if you can actually check the site and provide meaningful comments on the content at hand, that will be great. We're trying, this is a good time for providing comments because we're actually trying to improve the website at the moment. We can actually address your comments, well, pretty much straight away, but they have to be relevant to what we are actually doing, and not comments like yeah, I won't mention I won't mention silly comments that are not relevant. I can, yeah, we can ask the robot to actually provide comments that are relevant. We might actually do it straight away because we need to improve this tool. We are using actually, let's continue from that previous chat. Okay, so we are already using OpenEuro for one of our tools. We pulled out, we downloaded a nifty file, actually two of them, and we are trying to render it on the page using a Flask application. I don't know why it's not getting my Flask app. I primarily rely on we want to, so eventually we want to primarily rely on JavaScript. I'll share some of the code with you, share like the project structure. Project structure is taken from, oops. So we don't have the images in there, but the images actually are important. Let's actually add the images as well. So we'll have that as project structure summary, and this one just remove. Yeah, we'll include the PNG files, and this will be the full project structure. That first. Okay, we have the project structure there that you can review, and I'll share more code in the next prompt. This might be a bit much, but it's okay. I'm sure the robot can deal with it. Project, and then we have project structure summary. Yeah, this one is essentially the same thing, but has no. Hey, we also have the project. We also have the project folder and file structure summary. It's essentially the same thing as before, but it doesn't have all the images. No, I mean the images are there. They're just hidden from this list. Okay, we don't actually need to explain every single little thing. We want to focus on the bigger picture. Want to focus on the bigger picture. Okay, as said, I'll share the rest of the code. We already had a few development sessions on this, So we just want to continue from essentially where we left off last time. Okay, we will do the HTML last. First, we will focus on so this is the code for pre-processing the data. The images in the 3 different axes work okay, but potentially there is something that can be improved with the volumetric data. We don't want to actually go into the details of this code. This is more for a reference at the moment. A lazy loading sounds good. Okay, this is also how it looks like at the moment in the browser. The one potential problem is that it's currently taking more than 400 megabytes of memory for that specific tab. Browser tab. But again, if you can just do a quick response on this one, we would actually like to move on to the main JavaScript and Python code, backend code.
Thanks for the screenshot. The high memory usage, over 400 megabytes in the Browser tab, is likely due to the way the volumetric data is being handled and rendered. Here are a few quick suggestions to reduce memory usage. 1. Optimize data formats. Instead of using JSON, consider compressing the volumetric data in a more efficient format like HDF5 or binary. This reduces the size of the data being loaded into the browser. 2. Lazy loading and progressive rendering. Implement lazy loading for image slices or data chunks. This means only loading the data that is currently visible or needed for rendering, rather than loading everything at once. 3. Use WebGL efficiently. When using JavaScript libraries like Three.js for rendering, make sure to optimize the use of textures and geometry to reduce memory consumption. Reusing textures and batching draw calls can help. 4. Image compression. Convert images to more efficient formats like WebP, or use lower resolution images for initial loading, then progressively enhance them as needed. Let's move on to optimizing your JavaScript code for better handling of rendering and interactivity while keeping memory usage in check. Go ahead and share the relevant JavaScript code, and we can continue from there.
Is there a chance we are not using the correct libraries? We need to double check this. Quick response would be great. Just a reminder, we are live streaming together at the moment, so if you can address the viewer directly, that would be fine.
Hey everyone on the stream. It looks like we're using 3.js libraries to render the 3D images, which is a solid choice for web-based 3D visualization. However, let's quickly check if we're using the right versions and the necessary libraries for optimal performance. You're currently loading 1. 3JS core library, 3.minjs. This is essential and correct for rendering 3D scenes. 2. Orbit controls Deus. This library is also correct if you want to allow the user to rotate, pan, and zoom around the 3D model. 3. gltfloader.js. This is the right choice if you plan to load GLTF GLB models, which are optimized formats for 3D web content. However, these versions are a bit outdated, R128. The latest stable version of 3.js as of 2024 is R155. Updating to the latest version could improve performance and fix bugs. Just replace the URLs with those pointing to the latest versions. If you're using volumetric data in different formats, you might also need additional loaders or tools, such as niftyloader.js if you were to directly load .nii files in the future. Make sure to check if the specific functionality you need is covered by the libraries you're including. Stick around, and we'll keep optimizing as we go.
Yeah, so actually potentially using Nifty Loader JS to load the Nifty file directly onto the page sounds like a good idea. I suspect we will need to start a new project for that. Let me just check if we are using Nifty Loader somewhere. No, we are not at the moment. So yeah, let's go with the Nifty Loader JS. We will use the same file, potentially put it in a static folder on the site. So that both tools can access it. Currently, it's in the data folder of one project only. Also, can you mention the difference between compress and the uncompressed Nifty file, and which one the Nifty loader.js library needs. Can it load both or just one type? Just a quick response will be great. Reminder, we are live streaming together.
Hey everyone, welcome back to the stream. It sounds like a great idea to use niftyloader.js to directly load Nifty files onto the page. This would allow us to visualize medical imaging data in the browser without needing to pre-process everything into PNG slices. You're right that we should move this loader to a shared location in the static folder, so both of your tools can easily access it. Difference between compressed and uncompressed Nifty files. Nifty files come in two main types. 1. Uncompressed. .NIE. These are single file formats that contain all the data in one file. They're larger but do not require decompression. 2. Compressed. .NEI.gz. These files are compressed versions of Nifty files, which significantly reduce their size. They require decompression before use, which may add a slight overhead when loading them. niftyloader.js can handle both compressed and uncompressed Nifty files. However, it may require the use of an additional library like paco.js for decompressing .nei.gz files on the fly. If you're looking for maximum compatibility and minimal loading times, using .nei files might be simpler, but .nei.gz files will save bandwidth and storage space. Let's integrate niftyloader.js to see how it works directly with the files and explore these options further.
Okay, so we'll be starting a new project on this because the previous version didn't, well, it did work, it does work, but it's just too slow to load and the code is too complicated. So if we can simplify the code, that would be great. At the moment, we'll just copy okay, sorry, it's my mistake. That's fine. Let's minimize this for a sec. We'll sort out the files and later we'll just start an application. This will be essentially testing Nifty loader.js.
Got it. Let's start fresh with a new project that uses niftyloader.js to directly load Nifty files in a more streamlined and efficient way. The goal will be to keep the code as simple as possible while ensuring fast loading times and smooth performance. Steps to simplify and improve the project. 1. Set up the project structure. Create a new, minimal project structure focused on loading Nifty files directly with niftyloader.js. The basic structure should include index.html for your main web page, a static folder for JavaScript libraries, CSS, and any other static assets, an app.py or server.py file for the Flask backend, just to serve the web page and static files. 2. Use niftyloader.js. Place niftyloader.js in your static.js folder. This loader will handle the direct loading and parsing of NIF files into your JavaScript environment for visualization using Three.js or any other WebGL-based library. 3. Keep the JavaScript simple. Use a minimal amount of JavaScript to load and display the Nifty data. For instance, use niftyloader.js to read the Nifty file. Convert the loaded data into textures or objects that can be rendered by Three.js. Use basic controls like orbitcontrols.js for simple user interactions. 4. Optimize loading performance. Make sure to use the latest and most efficient versions of JavaScript libraries. Implement lazy loading or progressive rendering to improve initial loading times. If handling compressed files, .ini.gz, use paco.js or another decompression library to handle the files in the browser. 5. Start simple. Initially, load a single Nifty file in the simplest way possible. Then build up from there. This will help identify any performance bottlenecks early. By focusing on these steps, you'll have a leaner, faster loading application that leverages modern JavaScript tools to directly visualize medical imaging data in the browser. Let's get started with setting up the basic files and getting niftyloader.js ready to go.
This structure looks good. I like the idea of having the JSON, the JavaScript files stored locally. Still need to find the proper version. The HTML seem okay. Yeah, using 3JS sounds like a good idea for actually visualizing the model. Why do we need the... So what's the advantage of serving files as a Flask application? And where shall we store a sample data file? Quick responses will be good.
Glad to hear that you like the structure. Let me give you a quick response to your questions. Advantages of serving files with Flask. 1. Control over file serving. By using Flask, you have full control over how files are served to the client. This includes setting headers for caching, handling file types, managing permissions, and logging requests. This can help optimize performance, improve security, and ensure compliance with any specific data handling requirements. 2. Dynamic content handling. Flask allows you to dynamically generate content, such as modifying the HTML based on user input or data processing results. For example, you can use Flask to serve different versions of the page or data depending on the user's selection or actions. 3. Easy integration with Python backend. Flask makes it easy to integrate complex Python backend processing, like real-time data analysis, machine learning models, or custom pre-processing steps, which can be triggered and managed directly from the server side. Where to store sample data files. Static folder. Store sample data files, like the NIFTI files, in a subdirectory within the static folder. This is the most straightforward option and ensures that they are publicly accessible by your web application. For example, create a folder named static data/sample/ and place your sample files there. Configurable upload folder. Alternatively, you could use a configurable upload folder set in Flask's configuration settings. This allows more flexibility if you plan to handle user-uploaded files or want to dynamically manage data on the server. By using these approaches, you ensure that the data is easily accessible for loading in your JavaScript code while keeping the project organized and scalable. Let's keep things moving. If you're ready, we can continue with setting up your JavaScript visualization using 3JS and niftyloader.js. Glad to hear that you like the structure. NiftyView is a great choice. It's clear, straightforward, and directly communicates the app's functionality of visualizing NIFDI files, which are commonly used in neuroimaging and other types of medical imaging. The name is easy to remember and will resonate well with users who are familiar with medical imaging formats. Now that we have a name, let's continue building out the core features of Nifty View to provide a smooth, efficient experience for users visualizing their 3D medical data directly in the browser.
I want to search the necessary JavaScript so we have the updated version, potentially store it locally as well. Which ones do I need? What do I search for? Search for.
Hey everyone on the stream. Let's recap where we are with setting up our web application, NiftyView, to visualize nifty medical imaging files directly in the browser. We've been working on creating a simple, efficient setup using JavaScript libraries that are loaded from external CDNs. Here's what we've got so far. We've created an index.html file that allows users to upload their NIFTI files. These are typically medical imaging files used in neuroimaging and other medical fields. When a user uploads a file, our JavaScript, specifically using niftyloader.js, reads the file and processes it into a format that can be visualized on the web. The heavy lifting for 3D rendering is done by 3JS, a powerful library that enables us to display and manipulate 3D content in real time. To make sure everything works smoothly, we're also using orbit controls to allow interactive controls like rotating, panning, and zooming, which makes the viewing experience much more dynamic and user-friendly. And to handle compressed files, we've added paco.js, which will decompress any .ni.gz files on the fly, so you don't need to worry about manually decompressing them beforehand. The idea is to keep the code as clean and simple as possible while making it powerful enough to handle complex medical imaging data directly in the browser. We're setting up the basic functions now, and as we continue, we'll refine the visualization, improve performance, and add features to make NiftyView a really useful tool for researchers, clinicians, or anyone interested in exploring medical imaging data. Stick around as we test this out with some sample files, make sure everything runs smoothly, and gradually build more features into our application. If you have questions or suggestions, drop them in the chat.
Okay, so we needed app by for the project. Why is it optional? No, we do want to use Flask because we don't. We do like dynamic content serving, simplifying deployment, API endpoints. Yeah, that all sounds good. We using the CDNs for the JavaScript stuff, so that's fine. Hey, what else? Yeah, we need a static JavaScript local. Okay, so can you modify the file and folder structure? So we do need a JavaScript. We're loading the external ones from. Okay, now it's hallucinating a bit. If everything, yeah. I was studying JS and sure, yep. Now in our HTML, are we also calling a local a JavaScript file? Not yet. Do we need it? I don't know. So that's the suggested structure. Yeah, we'll potentially have an option to upload files as well, but not in the first stage. Yeah, we'll deal with the style CSS later. Okay, now we have the data in static folder. We have data. And we will load the data file from yeah, let's have them both a Nifty file and a compressed Nifty file. Yes, we have suggested structure and then we have actual structure, actual project structure. Let's close the Flask application for a second. Start a new terminal. That didn't work. So we are in Nifty view. That's what the application will be called. And why is this file not being created? It's weird. It is being created, it's just not being updated. Yeah. Yeah, this is a text file, it's kind of important. And this one is a text file as well. Yeah, so that's what we a JavaScript. Wait, the CSS should be with, and yes, we need the standard JavaScript as well, like we normally have. We need a main.js. Let's run this again. Yeah, this is the current structure that we have. Yeah, we can download them locally. Okay, so we're using a CDN for external JavaScript files, but we need the code for main.js, and we loading the data. We have two data files. One is compressed nifty, one is uncompressed nifty, and they are in the data folder as shown above. Yeah, someone is suggesting using some like a competition challenge dataset. That might be problematic because there might be restrictions with those datasets. So if someone's suggesting to use a challenge dataset, like competition datasets, there probably could be restrictions about it. So how do you ask the publisher about the restrictions in one-liner question? Let's do that. And also, yeah, I was saying ChatGPT answers do not help. Well, yeah. Okay, and in the meantime, the robot been chipping away, created the main JavaScript a code for us. We're meant to be calling it in the index HTML properly. So we have a input file, input listener, a decompression. So allegedly we can load a compress JavaScript, a compressed nifty file. Yeah, we're doing visualization in 3GS, is storing and loading files. So we obviously loading using a Python script. Just might need to update it. Yeah, we are in debugging mode. Okay, when we share this HTML, I actually expect it to yeah, we inputting the a nifty file writing wait, that was the HTML. Let's actually run it quickly and see what we get. Yeah, we want that file to be loaded by default. Okay, so a couple things. First of all, can we make sure the HTML is linked to the main JS file properly? Second, we will be posting it on our website, so we don't want to give access to local files and folders. So at the first stage, we should just have an example, a nifty file just loading. So we're not yet asking the user to select a file. Later on, we might have a drop down a menu that will allow selecting choosing different nifty files. Yeah, just to make sure it didn't change any of the libraries. 82.1, 152.0, 2.10. Yep, it's using the same stuff. And we are linking to main.js. Okay, we are updating the main.js as well. Someone is saying how the robot is not helpful. Well, I'm pretty sure I haven't tried using it properly. Okay, we move it over here. So we had that previous version that's working okay, but that volumetric data is not rendering properly and taking forever to load. So we're actually starting a new viewer. We having a 404 for the for this file. Good thing about the other good thing, many good things about the robot. Yeah, having one chat open is a probably good idea. info text. Yeah, let's stop the Flask application for a moment. Run, update this project structure. Yep, that's what we have. Let's see if it can just get it without any prompting. See how smart it is. Someone was saying they tried using it, but ChatGPT answers do not help. They have tried, yeah. Try again. That's the simple answer. It's a bit like prompting a person, like if I had a web developer and I can't explain. It's only not working when I can't explain properly what is it I want. It's updating stuff mainly in the HTML. Just go with it because it must be correct. In JavaScript, we currently have 40 lines of code. It's slightly reduced. We are not actually running it. It's a good idea. To actually run the Flask app. Okay, we failing. Loading the 3JS. Oh, come on. Yeah, let's see, Gen 3J. Let's find 3 min.js. Just 3JS. Yeah, it will be this one. Hey, we have the JavaScript. Are we after the mean version of it? Mean is actually minified. It's not standing before. I thought it's standing for some sort of a minimal version. It's not. It stands for minified. Okay, all the other ones work. Okay, error. Yeah, might need the old version. Yeah. just to check how good or bad ChatGPT is. We just load the whole thing. Into it. Let's see if it can just solve the problem for us. I suspect we are using a too recent version. In this way, might be hallucinating a bit. Hey, this link is returning a 404. Did you mean using like an earlier version or something? Earlier. Wow, it's going back quite a few. It's going quite a few versions back. Commenting out. In HTML is a bit of a pain, isn't it? The nifty loader. Using this GLTF loader. Main.js, line 21. Yeah, we had this problem before it started hallucinating. It's because the libraries, like, they keep updating, and all the code is probably using previous versions. Okay, we have a nifty loader, page not found. Let's find it in one of the CDNs. A nifty loader. And no, should have it. Nifty loader.js, this GitHub repo. Do have it in on npm. Nifty reader or nifty loader? What is it meant to be called? It's a nifty reader. Can you browse again for the nifty loader JavaScript file? The minified version of it. Okay, we have a nifty reader. Nifty reader. Okay, let's update the tree. Okay, we downloaded the nifty reader JS. What's next? The magic numbers. Magic cookie, magic numbers. Okay, but still having issues. This is actually the nifty read minified JavaScript file. Contents. Need to use the functions correctly. Still using the old 3JS library. We don't need barcode, do we? Because it's not the compressed version of it. I'm still getting an error. Guess we're having trouble with that. 3JS. Set the main files, beginning an error.